Be the biggest scientific quest going. Physics. It's had these incredible successes, but right now it's facing some truly massive mysteries. We're asking, what's really out there, just beyond what we currently understand about the universe?
It's a fascinating time, really, because we have these two giant pillars of understanding. First, there's the standard model of particle physics. Think of it as our quantum rule book. It covers three fundamental forces: strong, weak, electromagnetic, and all the elementary particles we know about. Its precision is just stunning. Remember the Higgs boson discovery in 2012? That was the final piece predicted by the standard model. A huge confirmation.
Right, the standard model on one side. And then the other pillar is Einstein's general theory of relativity, our best theory of gravity. It describes gravity not as a force, but as space-time actually curving. And it's passed every test bending starlight, predicting gravitational waves we've now detected. So these two really are the bedrock, aren't they?
They absolutely are. Individually, they're phenomenal achievements. But here's the big problem, the central conflict. They just don't work together. They're fundamentally incompatible. The standard model is quantum, but it has, no room for gravity. General relativity describes gravity perfectly, but it's classical. It knows nothing about quantum mechanics.
Okay. So this incompatibility, this clash, is what's stopping us from tackling the really deep questions, like what's actually happening inside a black hole, quantum-wise, or the very beginning, the Big Bang. And then there's dark matter and dark energy, this stuff that supposedly makes up 95% of the universe, but we can't directly see.
Precisely. That's why physicists are constantly searching for physics beyond the standard model, or BSM. It's not just, for fun. It's a scientific necessity.
Yeah.
We strongly suspect that both the standard model and general relativity, despite being amazing, are what we call effective theories.
Effective theories. What does that really mean? Like, they work, but only up to a point.
Yeah. Think of them like really, really good local maps. They work perfectly in their own domain, particle accelerators or planets orbiting stars, but they don't show the whole picture, the whole continent. They don't tell you what's beyond their borders. They're brilliant approximations, sure, but they hint at a bigger, more fundamental map we haven't found yet.
Okay, so today's mission is to explore beyond those maps.
Yeah.
To look for that more fundamental picture. Let's do it. We'll dive into the cracks in what we know, and then look at the wild ideas trying to bridge those gaps.
Right, so the push for new physics isn't just abstract. It comes from these really deep holes and inconsistencies in our current models. And what's really striking is how these problems often connect the tiny quantum world with the huge scale of the cosmos.
Absolutely. The standard model, for all its power, leaves some huge questions hanging.
What's the single biggest thing it just misses? The elephant in the room.
Oh, without a doubt, it's gravity. Just completely left out.
Yeah.
The standard model does a great job unifying other forces, but gravity, nope. Not there. And it's not like people haven't tried to just, tack it on. So why can't we just add gravity in? What goes wrong when you try?
Well, the math basically explodes. When you try to apply the standard model's quantum rules to gravity, you run into these uncontrollable mathematical infinities. It's what physicists call non-renormalizability. It's a giant red flag saying, this approach just doesn't work. We need something fundamentally different. Plus, the standard model gives zero explanation for why gravity is so incredibly weak. I mean, it's something like 10 to the power of 41 times weaker than the strong force. That enormous gap is part of this other puzzle, the hierarchy problem.
And speaking of huge puzzles, this always gets me. The stuff the standard model does, describe all the particles, all the energy we know, it only makes up about 5% of the total mass energy in the universe. Just 5%.
Incredibly humbling, isn't it? The other 95% is just dark. Unknown. About 27% of that is what we call dark matter. We can't see it, it doesn't emit light, but we know it's there because of its gravity. We see galaxies spinning way too fast, light bending around clusters in weird ways, gravitational lensing, that kind of thing.
The bullet cluster always comes up here as really strong evidence. Why is that one so convincing for dark matter?
Right, the bullet cluster. It's basically two galaxy clusters that smash into each other. What's amazing is you can see the ordinary matter, the hot gas, slowing down in the collision, glowing in X-rays. But when you map the total mass using gravitational lensing, you see that most of the mass just sailed right through without slowing down. That separation growing gas lagging behind the main clumps of gravitational mass strongly suggests that most of the mass is in some kind of invisible, collisionless stuff. Exactly what we expect from dark matter.
And the standard model. No particle fits the bill.
Okay, so that's 27% dark matter, then the other 68% dark energy. This bizarre force making the universe expand faster and faster. What's the issue there for the standard model? Ugh, this is where things get really bad. It's called the cosmological constant problem. Quantum physics actually predicts an energy for empty space, a vacuum energy. But when you calculate how much energy there should be based on the standard model, the number you get is, well, it's an astonishing 120 orders of magnitude larger than what we actually observe driving cosmic acceleration.
120 orders of magnitude, that's not just wrong, that's astronomically, catastrophically wrong. It means we fundamentally misunderstand empty space itself.
Exactly. It's often called the worst prediction in the history of physics. It's a massive failure when you try to connect the standard model to cosmology. We are deeply confused about the quantum nature of nothingness.
Then there's the hierarchy problem you mentioned. This huge gap between the energy scale where particles like the Higgs get mass, around 100 GeV or so, and the Planck scale, way up at 1019 GeV where quantum gravity should be dominant. Why is the Higgs so light compared to that?
It feels deeply unnatural to physicists. Quantum effects, these virtual particles flickering in and out of existence, should naturally push the Higgs mass way, way up towards that Planck scale. For it to be down around a 125 GeV, you need this incredibly delicate, almost unbelievable cancellation between two very large numbers. It's like trying to balance a pencil on its very tip perfectly to one part in 10 to the 34. It screams out for some new physics nearby, maybe around the TeV scale, to stabilize things. Otherwise, it's just a ridiculous coincidence.
Okay, what about neutrinos? The standard model originally said they were massless, but we discovered they change type neutrino oscillations, which means they must have mass.
Right. And while we can sort of patch the standard model, add mass terms by hand, and ad hoc fix, really it doesn't explain why they have mass or why their mass is so incredibly tiny compared to other particles. It's like sticking a plaster on a wound without knowing what caused it.
And the matter-antimatter mystery. The Big Bang should have made equal amounts, right? We should have just annihilated each other, leaving nothing but light. But here we are in a universe full of matter.
Yeah, for us to exist, there must have been a tiny imbalance, maybe one extra matter particle for every billion matter-antimatter pairs. The standard model does have a mechanism for this called CP violation, but the effect it predicts is just. It's many orders of magnitude too small. Way too weak to explain the universe we see. We need new sources of this asymmetry.
It feels like the standard model keeps hitting these walls. Plus, it has all those numbers, 19 free parameters, particle masses, force strengths, that it doesn't predict. You just have to measure them and plug them in. And why 3 generations of particles, like heavier copies of each other? No explanation for that either.
Exactly. All these things together, the arbitrary numbers, the unexplained patterns, the missing pieces like gravity and dark matter, they really make the standard model feel less like the ultimate theory and more like a remarkably successful but ultimately temporary description, a placeholder.
Let's shift gears to general relativity then. It also seems to break down, especially when you push it towards the quantum world. We mentioned the incompatibility, GR being smooth, quantum being jumpy. Why is that such a fundamental clash?
Because when you try to apply quantum rules to gravity's messenger particle, the hypothetical graviton, you hit those same uncontrollable infinities again. This problem of quantum gravity means our two best theories just cannot both be the final word everywhere. We need a theory that speaks both languages.
And GR even predicts its own failure points, doesn't it? These singularities, infinite density, infinite curvature, inside black holes and at the Big Bang itself. What are those, really?
Most physicists see them as mathematical artifacts signaling the breakdown of the theory. They're not real physical infinities. They're like general relativity throwing up its hands and saying, my equations stop making sense here. You need a better theory, a quantum theory of gravity, to figure this out. Getting rid of singularities is a key job for any candidate theory.
And GR has other weird spots too, right? Like energy not always being conserved globally. Think of cosmological redshift, where light loses energy as the universe expands. Where does that energy go? And something called the problem of time, when you try to merge it with quantum ideas.
Yeah, those are deeper conceptual issues. But what's really powerful is how all these cracks, the hierarchy problem, dark energy, singularities, quantum incompatibility, they're not isolated. They point in the same direction. They link the Higgs to quantum gravity, the vacuum to cosmology. It's a unified case saying, we need something deeper.
Okay, that sets the stage perfectly. Which brings us to part 2, the big quest for quantum gravity and unification. With all these problems, it's no wonder people have come up with some seriously ambitious ideas, often from very different starting points.
Absolutely. The big contenders you hear about most are string theory, which kind of comes from the particle physics side, trying to unify everything. Then there's loop quantum gravity, which starts from gravity itself, trying to quantize space-time directly, and supersymmetry, which is a key ingredient in string theory, but also a powerful idea on its own.
Let's tackle string theory first. The basic idea is completely wild. Fundamental reality isn't point particles, but these tiny, tiny, one-dimensional vibrating filaments of energy called strings.
It's a radical shift, yeah. The core concept is that all the different particles we see, electrons, quarks, photons, everything, are just different vibrational modes of these fundamental strings. It's often described as a cosmic symphony. Different notes or vibrations correspond to different particles. It's a very elegant way to unify the particle zoo.
And the magic trick I hear is that one specific vibration pattern of a closed string just automatically behaves like a graviton, the particle of gravity, so gravity just naturally pops out of the theory.
That's one of its biggest selling points, yes. It naturally incorporates a quantum description of gravity, which is exactly what we need. But there's a catch, a big one. This mathematical consistency comes at a price. String theory doesn't work in our familiar 4 dimensions of spacetime, 3 space, 1 time. It requires 10-dimensional spacetime, 9 space dimensions, 1 time.
10 dimensions.
Well,
Okay, obvious question. Where are the other 6? We definitely don't see them.
the idea is that those 6 extra spatial dimensions are compactified, curled up, essentially into incredibly tiny, complex geometric shapes. Think of something like a garden hose. From far away, it looks one-dimensional, like a line, but up close you see it has a second, curled-up dimension, its circumference. These curled-up dimensions in string theory are thought to be unimaginably small, potentially on the Planck scale, far too small for us to ever perceive directly. They're often modeled using things called Calabi-Yau manifolds. And here's the really wild part. The specific shape and geometry of those tiny hidden dimensions is what determines the physics we do see in our large extended dimensions. The particle masses, the force strengths, they're supposedly dictated by that hidden geometry.
But then, around the mid-90s, there wasn't just one string theory, there were 5. That seems messy for a theory of everything.
It did seem like a problem. But then came what's called the second superstring revolution. Physicists discovered these amazing mathematical connections, called dualities, linking all 5 theories. It turned out they weren't fundamentally different theories, after all, but rather different perspectives on a single, more fundamental underlying theory. Edward Witten proposed this deeper framework and called it M-theory. M-theory seems to live in 11 dimensions and includes not just strings, but also higher dimensional objects called membranes or brains. It suggests there's an even richer structure underneath string theory itself.
So stepping back, how does string theory actually help with those big problems we talked about, the clash between GR and quantum mechanics, for instance?
Well, by replacing point particles with extended strings, interactions aren't happening at single points anymore, they're smeared out. This smoothing effect tames those uncontrollable infinities that plague attempts to quantize gravity directly. So it offers a mathematically consistent theory of quantum gravity. It also has ways to incorporate the standard model forces, potentially explain the origin of particle families, and ideas like brane worlds, where our universe might be stuck on a membrane in higher dimensions, could even explain why gravity is so weak compared to other forces and provide candidates for dark matter.
Okay, now let's switch to loop quantum gravity, LQG. This takes a completely different tack, right? It doesn't start with particles and forces. It starts by trying to quantize space-time itself, directly from general relativity.
Exactly. It takes GR's message that gravity is space-time geometry very seriously. Its main goal is quantum gravity, not necessarily unifying all forces into one package. And its core prediction is really mind-bending. LQG predicts that space-time itself isn't smooth and continuous like we usually imagine. Instead, at the tiniest scales, the Planck scale, it has a discrete, granular, or atomic structure. Space itself is made of fundamental units.
Atoms of space. How does that even work? What are these atoms?
Mathematically, they're described by structures called spin networks. These are like abstract graphs with nodes and links. The nodes represent fundamental quanta of volume, tiny chunks of space, and the links represent fundamental quanta of area connecting them. So there's a smallest possible area, a smallest possible volume. You can't zoom in forever. And the evolution of this quantum geometry, how space changes over time, is described by something called spin foams. It's like a bubbling, fluctuating foam of geometry at the Planck scale.
One really cool result that comes out of applying LQG ideas to cosmology is the Big Bounce. What's that about? Instead of a Big Bang singularity.
Right. Loop quantum cosmology, or LQC, suggests that the universe didn't begin from an infinitely dense point. Instead, it predicts our expanding universe emerged from the collapse of a previous universe. As that previous universe contracted, when it reached incredibly high density, quantum gravity effects kicked in, creating a kind of repulsive force that caused it to bounce and start expanding again. This avoids the singularity entirely and gives a physical picture for the beginning.
Fascinating. Okay, third big idea, supersymmetry, or SUSY. This proposes a deep symmetry, but between matter particles, fermions, and force carriers, bosons. What does that mean?
It proposes that every fundamental particle we know has a heavier superpartner particle or sparticle that differs by half a unit of spin. So the electron, a fermion, would have a superpartner called the selectron, a boson. The photon, a boson, would have a superpartner called the photino, a fermion. Since we haven't discovered any of these sparticles yet, if SUSY exists, it must be a broken symmetry. This means the sparticles must be significantly heavier than their standard model partners, otherwise we'd have seen them already.
The most studied version is the minimal supersymmetric standard model, the MSSM, and it literally doubles the entire particle spectrum.
That sounds like a lot of new particles to find.
It is a lot. The MSSM also needs at least 2 Higgs fields instead of just one, and it often includes a new conserved property called R-parity. R-parity is important because it helps forbid things like protons decaying too quickly, which we don't see, and crucially, it makes the lightest supersymmetric particle, LSP, stable.
And this stability is key, but first, the hierarchy problem, that unnatural lightness of the Higgs, this is what SUSY is famous for potentially solving, right? This is really its prime motivation. Remember those quantum corrections that should make the Higgs heavy. In SUSY, for every loop of standard model particles contributing to the Higgs mass, there's a corresponding loop of their superpartners. And crucially, these contributions come with opposite signs. So, contributions from sparticles naturally cancel the problematic contributions from standard model particles. If the sparticles aren't too heavy, maybe around the TeV scale, this cancellation works beautifully to keep the Higgs mass light without any extreme fine-tuning. It's a very elegant solution. Plus, adding all these sparticles changes how the strengths of the fundamental forces evolve with energy. It turns out that in the MSSM, the strengths of the strong, weak, and electromagnetic forces, which are very different at low energies, evolve in just the right way to meet at a single point at very high energies. This gauge coupling unification is another hint that SUSY might be on the right track.
And that stable LSP you mentioned, the lightest superpartner, that sounds like a dark matter candidate.
Exactly. Because our parity makes it stable, it can't decay into ordinary particles. So LSPs created in the hot Big Bang would still be around today as cosmic relics. If the LSP is also electrically neutral and interacts only via the weak force, which many candidates like the neutralino are, then it has precisely the properties needed for a cold dark matter candidate. It's a fantastic bonus. A theory motivated by the hierarchy problem naturally provides a candidate for dark matter.
Okay, shifting gears now into part 3. We're looking at some alternative ideas, maybe less theory of everything, and more focused on solving specific big problems like dark matter.
Right, and one of the most prominent and definitely controversial alternatives to dark matter is MOND, modified Newtonian dynamics. Proposed by Mordechai Milgram, MOND doesn't invent a new particle. It suggests that gravity itself behaves differently than Newton or Einstein predicted, but only in the regime of extremely low accelerations. Think the far outer edges of galaxies. It introduces a new fundamental constant of nature, a zero, a tiny acceleration value, and says below that threshold, gravity is actually stronger than expected.
And MOND has had some really striking successes, hasn't it? Especially when looking at individual galaxies. I hear it predicts those flat rotation curves without needing any dark matter at all.
It does, and that's its biggest claim to fame. It also makes a very precise prediction for the relationship between a galaxy's total baryonic mass, stars and gas, and its rotation speed, the baryonic Tully-Fisher relation. And observations match this prediction with remarkably little scatter, often better than standard dark matter models initially predict. It also naturally explains other observed relations like the radial acceleration relation and why low surface brightness galaxies seem to have so much dark matter according to standard models. On galactic scales, its empirical record is impressive.
But there have to be buts. Where does MOND run into trouble?
The main issues arise when you look at larger structures, like galaxy clusters. MND significantly reduces the need for dark matter there, but it usually fails to fully account for the mass discrepancy. You still seem to need some unseen mass, maybe hot gas or massive neutrinos, what some call phantom matter. And the bullet cluster remains a major problem. That visible separation of gravitational mass from baryonic mass is very hard for basic MND to explain naturally. It really looks like collisionless dark matter. Plus, original MND isn't relativistic, it's a modification of Newton. Making it compatible with general relativity has proven very difficult. Theories like TeVe's exist, but they're often complex and struggle to match cosmological observations like the cosmic microwave background patterns or the large-scale structure of the universe. Things the standard lambda CDM model with dark matter and dark energy explains very well.
Okay, another idea tackling the hierarchy problem, but in a different way. Warped reality, extra dimensions, the Randall-Sundrum model. How does warping dimensions help with the Higgs mass?
This is a really cool geometric idea. Imagine our universe is a four-dimensional brain, like a sheet living inside a higher dimensional space, maybe 5 dimensions, called the bulk. In the Randall-Sundrum model, standard model particles are stuck on our brain, the TeV brain, but gravitons, can travel through the 5D bulk. The key is that this extra dimension isn't flat, it's warped, meaning space-time is curved exponentially. This warping concentrates gravity strongly near another brain, the Planck brain, and makes it fall off very rapidly as it travels through the bulk to reach our brain. So gravity seems incredibly weak to us because we only feel the tiny red-shifted tail end of it that leaks across the warped dimension. This geometry naturally generates the huge hierarchy between the Planck scale and the TeV scale without fine-tuning. And it predicts detectable signatures like heavy Kaluza-Klein KK modes of the graviton.
Then there's Sir Roger Penrose's idea, conformal cyclic cosmology. CCC. This one sounds really mind-bending. The universe goes through infinite cycles or eons.
It's definitely highly speculative, but elegant. Penrose considers the very far future of our universe. Trillions upon trillions of years from now, after all stars have died, black holes have evaporated via Hawking radiation, and only massless particles like photons are left, flying through an incredibly dilute, cold, vast space. He argues that this far future state, where mass and scale become essentially meaningless, is mathematically conformally equivalent to the hot, dense, infinitely small state of a Big Bang. So the end of one eon smoothly becomes the beginning of the next. The universe effectively forgets its size and temperature and starts over. It provides a potential escape from the Big Bang singularity and suggests a potentially endless cycle. He even speculates that some information might pass between eons.
Wow, does it make any testable predictions? Can we see evidence of a previous eon?
Yes, and this is crucial. Penrose predicts that the evaporation of supermassive black holes from the previous eon should leave faint imprints on our cosmic microwave background radiation. These would look like anomalous, energetic hotspots surrounded by concentric circular patterns of low temperature variance. He calls them Hawking points. Finding these would be stunning evidence.
Have they been found? And I feel like I would have heard about that.
Well, Penrose and collaborators have claimed to find tentative evidence. However, these claims are highly controversial. Independent analyses by other cosmologists have generally concluded that the patterns found are statistically consistent with random fluctuations expected in the standard CMB map. So the jury is very much still out. Most experts are skeptical right now.
All right, let's move into part 4, the theoretical crucible. Even these really clever ideas like string theory and LQG face their own internal problems, right? It's not just about matching experiments.
That's right. String theory, for instance, ran into a huge conceptual challenge. The initial hope was it would uniquely predict our universe, our specific particle masses and forces. But that didn't quite pan out. It led to what's known as the string theory landscape, or the 100 and 500 solutions problem.
10 to the 500, that number again. What does it mean here? Is that the number of possible universes string theory predicts?
It's roughly the estimated number of different ways those extra 6 dimensions can be compactified, curled up in a stable or long-lived way. Each different way of curling them up, each different vacuum state, results in a different set of physical laws, different particle masses, different force strengths in the resulting 4 dimensions. So instead of predicting one universe, string theory seems to predict this vast landscape of perhaps 100, 500, or even more possible universes, each with different physics.
Okay, that completely changes the game. If it describes potentially any universe, how can you test it? How does it predict our specific universe?
That's the core criticism. It makes string theory seem less predictive and more descriptive. Some critics argue it's become a theory of anything, because with so many possibilities, you can probably find one that matches whatever you observe, making it hard to falsify.
This is where the anthropic principle comes in, isn't it? The idea that, well, maybe all these universes exist in some multiverse, and we just happen to live in one where the laws and constants allow life, stars, and galaxies to form.
Exactly. Proponents like Leonard Susskind argue that the landscape isn't a failure, but a prediction of a multiverse. We find ourselves in a universe with, say, a small cosmological constant, because in universes where it was large and positive, galaxies never formed, and in universes where it was large and negative, they collapsed immediately. No observers could arise there. But this is highly controversial. Many physicists dislike it because it feels like giving up on explaining why the constants have the values they do from fundamental principles. It relies on the existence of other universes we can't observe, making it seem potentially unscientific to critics. It's a huge philosophical debate within the field.
So, as a kind of reaction to this landscape problem, there's the swampland program. What's that trying to do? Is it trying to map the landscape?
Sort of the opposite, actually. The Swampland program tries to figure out which mathematically possible theories of quantum gravity are actually impossible to realize consistently. It aims to identify universal principles or constraints that any valid theory living in the landscape must obey, separating them from the inconsistent theories that reside in the swampland. It flips the question. Instead of asking what's possible, it asks what fundamental principles constrain any theory that includes quantum gravity.
What kind of principles are we talking about?
There are several swampland conjectures. For example, the no global symmetries conjecture states that any symmetry in a consistent theory of quantum gravity must be a gauge symmetry tied to a force exact global symmetries are forbidden. Another famous one is the weak gravity conjecture, WGC, which roughly says that for any force, gravity must be the weakest force acting on at least one particle carrying that force's charge. This has implications for things like black hole decay. There's also the distance conjecture about what happens when you move very far in the space of possible theories, predicting infinite towers of light states should appear.
And one of the most debated is the de Sitter conjecture, right? It touches on dark energy.
Yes. This conjecture suggests that it might be difficult or impossible to construct stable or even long-lived metastable de Sitter vacuole universes, like ours, with a positive cosmological constant driving accelerated expansion within a consistent framework of quantum gravity, like string theory. If this conjecture holds true, it could imply that our current phase of cosmic acceleration driven by dark energy must be temporary, that dark energy is perhaps some evolving field like quintessence rather than a true constant, and might eventually decay. This would have profound implications for the ultimate fate of the universe. The overall goal of the Swampland program is to find these universal constraints to regain some predictive power, even within the context of the landscape, by ruling out large classes of seemingly possible theories.
Loop quantum gravity avoids the landscape, but it has its own major challenges. You mentioned the semi-classical limit being the biggest one. What is that?
Right. LQG starts by predicting this discrete atomic structure of space-time at the Planck scale. The single greatest challenge is proving rigorously that when you zoom out, when you look at scales much larger than the Planck scale, this granular structure correctly averages out to reproduce the smooth spacetime of classical general relativity that we observe and that works so well. It's surprisingly difficult to show how the smooth, continuous world emerges from these discrete quantum building blocks. How do those atoms of space collectively behave like the spacetime described by Einstein? That connection is still not fully established.
And what about defining how things evolve in time and adding matter?
Yeah, defining the dynamics specifically, solving what's called the Hamiltonian constraint, which governs time evolution in a background-independent way, is technically very challenging in LQG. And incorporating the standard model particles and forces is another major hurdle, especially getting particles with chirality, like left-handed neutrinos and right-handed antineutrinos into the theory often leads to technical problems like fermion doubling, where unwanted mirror image particles pop up in the math. Integrating matter realistically remains a work in progress.
Okay, so we have all these incredible theories, all these internal debates, but ultimately physics is an experimental science. Which brings us to part 5, the experimental frontier. Where are we looking for actual evidence?
It really is a global, multi-pronged attack. We're pushing the energy frontier with colliders like the LHC, trying to create new particles directly. We're probing the precision frontier, looking for tiny deviations from the standard model and very precise measurements. And we're exploring the cosmic frontier, using the universe itself from gravitational waves to the cosmic microwave background as our lab.
The Large Hadron Collider at CERN has been the flagship of the energy frontier. A huge part of its mission, after finding the Higgs, was searching for supersymmetry. What would a Suez-Y signal actually look like in the detector?
Well, the classic signature people looked for involves producing heavy particles like squarks, superpartner quarks, or gluons, superpartner gluons. These would decay very quickly through cascades of lighter particles, eventually ending up producing the lightest supersymmetric particle, the LSP. Since the LSP is stable and weakly interacting in most models, it would fly out of the detector unseen. So the signature would be events with lots of high-energy jets from the decays, maybe some leptons, electrons, or muons, and crucially a large amount of missing transverse energy that seems to have just vanished because it was carried away by the invisible LSPs.
What LHC has been running for years, smashing protons together trillions of times. Have we seen any sign of this missing energy signature for Suzy Y?
Frustratingly, no. Despite years of searching, the LHC experiments have found no evidence for supersymmetry. They've set very strong lower limits on the masses of many starticles. Squarks and gluinos, if they exist, must generally be heavier than about 2 TeV, trillion electron volts, and the partners of electroweak particles heavier than several hundred JeVs. This lack of discovery put significant pressure on the most natural versions of Suzy Y, the ones that solve the hierarchy problem most elegantly without fine-tuning, usually predict particles within the LHC's reach. So if Suzy Y is real, it's either heavier than we thought, unnatural, or hiding in more complex ways.
Does the LHC look for other things too, like the extra dimensions from Randall-Sundrum?
Oh yes, they search for the predicted Kaluza-Klein, KK gravitons, those heavier copies of the graviton that could exist in the extra dimension. These would appear as bumps or resonances in the energy distribution of particle pairs like electrons or photons. So far, nothing's seen, pushing the limits on their masses up to several TeV as well. There are even more exotic searches, sometimes trying to directly falsify certain theoretical frameworks. For instance, searching for particle configurations forbidden by string theory, like a hypothetical 5-plet of Majorana fermions, which might leave a bizarre track that suddenly disappears mid-detector. Again, no such events have been found. The universe, so far at the LHC, looks stubbornly like the standard model plus a Higgs.
Beyond colliders, you mentioned gravitational waves. This is a completely new way to test fundamental physics, isn't it?
Absolutely. The direct detection of gravitational waves by LIGO, Virgo, and Kagura is revolutionary. It gives us unprecedented tests of general relativity in the most extreme environments, like merging black holes and neutron stars. As these detectors get more sensitive, especially with future upgrades in next-generation observatories like LISA in space or the Einstein telescope underground, we could potentially detect tiny deviations from GR's predictions. Maybe gravitational waves don't travel exactly at the speed of light, or maybe they disperse slightly as they travel. Any such effect would be a smoking gun for new physics, possibly related to quantum gravity or dark energy.
And cosmology and smaller experiments still play a big role.
A huge role. Precision measurements of the cosmic microwave background, like with the Planck satellite or future missions, and mapping the large-scale distribution of galaxies with surveys like DSI or Euclid, provide incredibly powerful constraints on theories of dark matter, dark energy, and the early universe. And there's a big surge in smaller, agile experiments, often using cutting-edge quantum sensing technologies to hunt for specific dark matter candidates, like axions, or to test fundamental principles with extreme precision. It's not just about brute force energy. Clever, precise tabletop experiments are crucial too.
Looking ahead, what are the plans for the next generation of big machines?
At the energy frontier, the main vision currently discussed is the Future Circular Collider, FCC, at CERN. This is a massive project, potentially a 90-100-kilometer tunnel. It's planned in 2 main stages. First, FCCE, an electron-positron collider designed as a factory for producing millions of Higgs bosons, ZIB bosons, W bosons, and top quarks for extremely precise measurements. Then, in the same tunnel, FCCH, a proton collider aiming for energies around 100 TeV, 7 times the LHC's energy, offering massive discovery potential for new, heavy particles.
And there's also the International Linear Collider, ILC, proposed in Japan. What's its focus?
The ILC is conceived as a high-energy electron-positron linear accelerator. Unlike the circular proton colliders, it offers very clean collisions. Its primary mission is to serve as a Higgs factory. By colliding electrons and positrons, it can produce Higgs bosons in a very clean environment and measure their properties, how they interact with other particles, even how they interact with themselves with extraordinary precision, aiming for sub-percent level accuracy in many cases. The goal is to find minute deviations from the standard model predictions, which could be indirect signs of new physics.
And beyond colliders, things like the Event Horizon Telescope are getting upgrades too.
Yes, the next generation Event Horizon Telescope, NEHT, aims to produce much sharper images of black hole shadows, allowing for even more stringent tests of general relativity in the strong gravity regime. Plus, there are proposals for space-based quantum sensors, atom interferometers for detecting gravitational waves or ultralight dark matter, and ever more precise tests of fundamental symmetries and the equivalence principle. The search is becoming incredibly diverse.
So we really are at this fascinating point. We have these incredible theories, the standard model and general relativity, that work beautifully in their own domains. But they fundamentally clash, and they leave these huge cosmic puzzles, dark matter, dark energy, the beginning of the universe completely unanswered.
And in response, we have this amazing theoretical landscape filled with powerful, mathematically sophisticated, and conceptually revolutionary ideas. String theory, loop quantum gravity, supersymmetry, MOND, extra dimensions, trying to paint a bigger picture.
But then there's the experimental side, a stark and frustrating lack of direct experimental confirmation for most of these new ideas, especially from the LHC. It's found a universe that looks, well, remarkably like the standard model, just with this one extra Higgs particle. This forces some really tough questions, leading to these controversial ideas like the landscape and the anthropic principle. It feels like we have lots of maps to hidden treasure, but we keep digging where X marks the spot and finding mostly sand.
That's a good way to put it. The path forward is definitely uncertain, maybe more uncertain than it's been in decades, but it's absolutely a path of vigorous and diversified exploration. We're pushing on all fronts. And maybe the next huge breakthrough won't come from just one giant machine finding one new particle. Maybe it won't come from a single decisive experiment, but from piecing together clues, a synthesis of information from multiple frontiers, combining data from colliders, cosmic surveys, gravitational wave detectors, precision measurements.
So here's a final thought to leave you with. What if the universe's biggest secrets aren't hiding behind one single discovery, one new particle, or one grand theory? What if the answers lie in the subtle connections, the interwoven patterns that only become visible when we combine all these different ways of looking at the cosmos, from the highest energies to the largest scales to the most precise measurements? Are we maybe on the verge, not just of finding new physics, but of finding a completely new way to understand reality itself?